the direct comparison test. Let a sub n and b sub n be finite positive terms decreasing to 0, such that a sub n is less than or equal to b sub n for all n greater than or equal to some number n. If the series a sub n diverges, then the series b sub n diverges also. But if the series B converges, then the series of A converges also. Why is this? Let's look at this first one here. If A sub n diverges, where A is a series of finite positive terms, that means that A sub n is going to infinity. But we know that a sub n has smaller values than b sub n, which implies, of course, that b sub n, the series, has a greater value than a sub n, the series. So if a sub n goes to infinity, and the series of b sub n is at least as big, I know that b sub n diverges as well. Similarly, if the series b sub n converges, that means the series approaches some finite value. And since the terms of A are smaller than the terms of B and positive, that means that the series of A has a smaller value, but still positive, than the series of B, which implies that the series for A is finite as well. Now, what could we say if a sub n converges? Meaning it goes to a finite value. What does that tell you about b sub n? Well, it doesn't really tell us anything, because b sub n is greater than a sub n, which means it could still be finite or it could be infinite. There's a similar case if b sub n diverges. What does that tell us about a sub n? Well, it doesn't tell us anything. Just because the series of B is infinite, a sub n is less than that, so it still could be infinite or it could be finite. So the only two cases we need to worry about are here and here. In practice, I do not use the direct comparison test very often. There are usually better tests, but we haven't learned them yet. So for now, let's do some practice using the direct comparison test. Let's look at the series from 2 to infinity of 1 over n minus 1. Notice that n minus 1 is less than n. In fact, it's 1 less than n. So if I do the algebra, that is, if I divide both sides by the respective parts, I get 1 over n is less than 1 over n minus 1. So let's look at the p-series 1 over n. I know that the p-series diverges when p equals 1, which means the sum is infinite. But since the terms of 1 over n minus 1 are bigger than the terms for 1 over n, the summation for 1 over n minus 1 is greater than the summation for 1 over n. Which means, by the direct comparison test, my series diverges. I could do a similar thing for the series n equals 3 to infinity of 1 over the natural log of n. This one's a little bit harder to see unless you have some experience, or maybe you can think through it pretty easily, but once again, I know that the natural log of n is less than n, which means 1 over n is less than 1 over the natural log of n. From the previous example, 1 over n diverges to infinity. So by the direct comparison test, 1 over the natural log of n, which has bigger values than 1 over n, also must diverge to infinity. Now this example, the first one, for future reference, I would not use the direct comparison test. You could, but I really wouldn't. This one, I would, as well as our final example. So let's take a look at the series from 1 to infinity of the absolute value of the cosine over n squared. Taking a look first at a known series, 1 over n squared. This is a p-series where the power is 2, which is greater than 1, which means that this series will converge by the p-series test, of course. But remember that the absolute value of the cosine is always less than or equal to 1, which means the absolute value of the cosine over n squared is always less than or equal to 1 over n squared. So our unknown series has values or terms that are smaller than the values of a known series. And since the known series converges to a finite value, and my terms of the unknown are smaller, then the series itself has a smaller value and positive than the p-series that we compare it to, which means our unknown series must converge. And it converges by the direct comparison test.